All right. Welcome, everybody, to Standing for Truth. My name is Donny Budinsky, and I am your host for this afternoon's exciting program where we explore the incredible evidence for the global Genesis flood. On Standing for Truth, we uphold the truth of biblical creation. It is a privilege to have Ryan Thompson, a geoscientist, with me to assist in accomplishing this valuable mission. Ryan's presentation this afternoon is titled Noah's Flood, Rising Mountains and Sinking Valleys. This is part one of an important two-part series, and this program specifically discusses several important points. These points include how fractures and faults form due to stresses in the earth, how fracture data from across the Rockies only supports a single catastrophic event through the entire geologic column, and the geology of the Holy Land and how the Bible stories tell us about the type of stresses present in that region. If you are a skeptic of the global Genesis flood, you might just have your mind changed here tonight after watching this incredible show. Ryan, my brother, it is great to have you here. How are you doing tonight?
Fantastic, Donnie. Thank you so much for having me on. I'm very happy to be here and support your ministry and what you do and getting the word out there. So thank you.
It's my pleasure, Ryan. I am excited for this. I know the audience is as well. And part one here is going to do a great job at setting the foundation for part two, which we have scheduled next month. And so, Ryan, what I'd like to do for anybody who might be unfamiliar with who you are, as it is your first time here on Standing for Truth, is give you a formal introduction. Ryan holds a Master of Science degree in geoscience and worked for over a decade in the petroleum industry. After living in the Holy Land with his wife and two teenagers, they now live south of London, where he teaches and writes. He is an avid student of the scriptures, finding and sharing parallels between these two passions. In other words, Ryan, you're more than qualified to be speaking on tonight's topic, Noah's flood, rising mountains and sinking valleys, and also next month's talk, Revelation and geology. And so to the audience, we are doing this live as usual. We want to be interactive with you guys, and we want to address your questions. Perhaps you have clarifying questions. If you're a critic out there or a skeptic, we love you guys. We love when you're here. It helps us to plant some seeds. It also helps us to leave no stone unturned, which is what we want to do. So if you have a challenge, a question, an objection, feel free to send those in as Ryan is giving his presentation, which I'm excited for. I will do my best to see those questions and those comments, save them, and we'll spend some time after the presentation engaging them. So Ryan, let's hand it over to you, brother. And whenever you're ready, I can get your slides up and we'll get into your talk.
Yeah, sounds great. Thank you, Donnie. All right. So yeah, as Donnie said, I'm a geologist, geoscientist, worked in the oil industry for a while. And I'm a creation scientist is what I do in my spare time now. I teach online high school and high school geometry and chemistry and physics for homeschoolers all around the world, mostly Americans. But my hobby is not so much creation scientist looking back at Genesis and the flood, although I've done that, and looking at data to support a global catastrophic upheaval. But the twist with me is let's look instead at the future geologic catastrophes that are coming in the book of Revelation. So this today is just kind of a laying the foundation, right? So that we can understand and talk about fractures and faults, because they play a big role in what could be coming up. And so if you have a chance, you can pick up my book. It's out there on Amazon, or you can use a QR code there and go and, have a thumb through it and come ready in June for part two, where we'll, dive in and you'll have a lot more questions ready, I'm sure, at that point. So today we're going to stick with the geology of the Rocky Mountains, the Western US, and then, next time we'll talk about geology and revelation. But if we want to do another one on geology of the Holy Land, I am game for that. So that sounds fantastic, Donny. So let me see, advance my slides here. There we go. So if I were to give this like a fancy scientific title, I'd say something like fractures, indicators of a single catastrophic upheaval and its subsequent collapse. So, but what this is really saying, right, is that the fractures that I studied back in my master's degree and then later on in the oil business, they all, it's a tremendous data set that all points to one catastrophic event. You know, you go out and you see these animations of what the world looked like, you know, plate tectonic history as the plates move back and forth through time, right? And you kind of impress that it's cyclic, right? You have a supercontinent that is broken up and is formed what we know today as our various continents and their present configuration. But you reverse that, right? You put them together and then you break them apart again. You put them together, break them apart, put them together, break them apart, and all these different, you know, ideas of, you know, into deep time, right? And we don't see that in the fracture data. We don't see continents colliding and then splitting apart and then colliding again in another orientation and splitting apart again. We don't see multiple supercontinents being formed within the, what I would say, the Phanerozoic, right? The Cambrian to the modern rocks, the Cambrian to Quaternary. And so it really kind of leaves one to think, okay, maybe that entire geologic column where we find the bulk of the fossils, you know, I'm not talking about Precambrian and older rocks, but where we find the bulk of the fossils, maybe that really did happen during a single catastrophic event, you know. And can we look at data besides, I know you've had John Baumgartner on here before, right? Besides just his data and his model, is there actual data from the rocks that supports that catastrophic plate tectonic model? So that's what I'm going to share with you today. So, but first, I just kind of want to introduce you to what I call Bible tectonics. All right. So in Psalms 104, verse 8, there's a verse that says, the mountains rose and the valleys sank down. So that's where I got my kind of easy to remember title for today. And I believe this is talking about crustal shortening. So you have compression as the continents were slammed together at the end of this runaway plate tectonics, right? And that just brought the mountains up and allowed the continents to drain off the floodwaters into newly created ocean basins. All right, so we've got that process going on. After the flood, for the first few hundred years, what we see, even down to the time of Job, talks about the mountain collapses and crumbles away. I believe this is talking about not only erosion, but also post-orogenic extension as the crust returned to equilibrium. And then in the future, and this will be episode 2, right, where we talk about Revelation, where every mountain and island is moved out of its place. More faulting and tectonic movement right there for you. So a renewed heightened extension, right? Right now we're kind of in a lull, right? There isn't a lot of extension going on in the crust right now. There's really not a lot of earthquakes going on, although they do seem to be increasing, right? We're going to talk about how they're going to just increase exponentially as renewed extension just comes back, and how that could lead into the signs of Revelation and eventually maybe even the lake of fire. So hope you guys come back around for that. So here's a map of the Western United States, right? And this stretches from the Canadian to the Mexican borders. And you can see right in the heart there, from Montana down to New Mexico, is the Rocky Mountains, right? And so we're going to be talking about how the Rocky Mountains rose. And it's something we call the Laramide orogeny. All right, orogeny, oro meaning mountains, and gene from Genesis, beginnings, right? So this is the beginning of mountains. And the Laramide being named after the Laramie Formation in Laramie, Wyoming, from which, you know, we have a lot of data that indicates that the orogenic event actually occurred as the Laramie Formation was being laid down. So hence the Laramide. So this occurred as the Atlantic was opening up. And we had the North American plate colliding with the Pacific plate, okay? And as they're colliding, right, they're shortening kind of in this east-northeast direction. So you have northeast, right, and then you have a little more east of northeast, and that's the notation I'm talking about here. That's your mean Laramide direction, designated by this big yellow arrow on your screen, and you'll see the Greek letter sigma there, and H. Sigma is what us geologists use to refer to the maximum stress, and so H just means horizontal stress. So this is shortening direction. Kind of think of it like pushing a rug up against the wall, where you're going to end up with all these crenulations in the surface of the rug, right? And below the rug is kind of a slip plane, right? It's slipping across your wooden floor, and that'd be like your fault, and then you've got all these folds there, right? And that's how the mountains, to describe it in kind of lay terms, how the mountains were uplifted in rows. So this began in the Cretaceous and ended in the Eocene. And then this was followed by post-Laramide extension and collapse. So these mountains actually did start to collapse, right? They rose up, but they're not as high as they used to be. The edges did collapse. And so we'll talk about that, just as Job kind of indicates. So we got 3 study areas. Central Wyoming, the Wind River Basin, which was my master's degree, where I collected a bunch of fracture data out there. I'll show you that. And then West Texas, the Permian Basin, good old Permian Basin, where the American oil industry does most of its work these days, and it's the #1 oil producing region in the US. So we're going to go into the subsurface there and look at subsurface data there. And then we'll talk very briefly about some really cool sandstone dikes. So hope you stick around to the very end, because those sandstone dikes just really put the nail in the coffin of this model of deep time. So I'm excited to share that with you guys as well. So, all right. So fractures, what do they tell us, and how can we use them, right? That's kind of the big question. So I want you to understand fractures a little bit more before we talk about how we use them. We have 2 kinds of fractures. All right, we've got joints and faults, and there's 3 kinds of faults. But joints are fractures with no slip. All right, fractures or faults are fractures with slip, right? So a fault is what you're going to have an earthquake moving on, right? And there's 3 types. There's normal, strike slip, and thrust faults. All right, so I've got these block diagrams on your screen right here. You can see the joints on the left in the green, and then on the right of the screen, you can see an outcrop of rocks. It's kind of a flat pavement. You can see these big kind of through-going fractures. Those are joints, right? We're not talking about the little fractures at the edge of this outcrop as the rock kind of is falling off into the canyon. But the big through-going tectonic fractures are related to the stresses. All right, the normal faults in the first one here in the block diagrams, you can kind of picture almost the Dead Sea Rift Valley right there, right? You can picture the Dead Sea at the bottom of that with these normal faults along each side. That's a classic Rift Valley setting where you have extension. So normal faults are a result of extensional stress. Strike slip be like your San Andreas out in California, and that's the middle one. And then the far right one is thrust faulting. And so with thrust faulting, instead of the blocks being dropped down like a rift valley, right? The sides are moving apart and the middle is dropping down. In thrust faulting, you have horizontal compression and shortening, right? So this is like the rug up against the wall example, where you've got the mountains rising, okay? Because your maximum stress is the horizontal one and your least stress is the vertical, which allows the mountains to just pop right up there. Then the circle diagrams are just kind of how we plot these things, right? So you can get an idea of the orientation of the fractures using these diagrams. So when it comes to fractures and collecting fracture data out there, we actually just go out with a compass and measure the fractures. And what you'll see is you'll have kind of 2 sets, right? Just like in the Jordan Dead Sea Rift Valley, you have 2 sides of that valley, and they're kind of sloping down the faults on either side. And so those come to an acute angle, right? And the bisector of that angle is the stress direction. So we can look at the fracture geometry and determine the tectonic stresses that create those faults. And the real key thing is that we can go out and we can measure little tiny faults with hardly any offset on them out in outcrop, and we can measure hundreds and thousands of those, as many as we can find. And they all have the same orientation as the big faults that cause earthquakes and bring up whole mountain chains or create rift valleys. So mountains rise on these thrust faults, all right, and they may have some strike slip component. Okay, you've got this ramp, right, and you may have some strike slip components. They can be kind of complex. Okay, But we can sort that out by going out and collecting fracture data. So my thesis advisor, when I was in school, he'd already been teaching for 20 plus years, and one of his more recent students compiled the database of all of his previous students' fracture data. And it came to like 21,000 fractures that they had gone out in the field all across the Rocky Mountains and measured. They compiled that into this summary map that you see here on the right. And it's an amazing data set that he spent most of his career. This is Eric Ursula at Colorado State. Spent most of his career compiling a very compelling data set that supports catastrophic plate tectonics and the fracture record associated with that, despite being ardently against, right, anything to do with creation in a global flood. Amazing how that works, right? So anyway, what you see here is all these blue arrows represent locations where many, many fractures were measured and taken from. And then that kind of all just gives us that there's kind of this mean or overall east-northeast directed trend of shortening that's consistent with the, the North American plate colliding with the Pacific, okay, and bringing up these mountains along these ramp-like thrust faults. And there is, again, like I said, there is some complexity to that system where you have some ramp-like thrust faults that aren't exactly perpendicular to the shortening direction. And so on some of those, you have strike slip components as well. So it does get a little bit complex. And that was my thesis area that I went and studied in the central Wyoming. And it's kind of a little more east-west than the average kind of northwest trending mountains and intervening basins. So we'll kind of talk about that a little bit, because it really sets up and having that complexity. In fact, without that complexity, we wouldn't really understand as much of what was going on, right? But when you have complexity, it allows you to really nail things down a lot better, like a key in a lock, right? You're not just going to have a nice smooth key in a lock, because then anyone could open your door. But when you have a key that matches the lock, then you can unlock a door that can, and in this case, unlock some knowledge, right? Additional knowledge you couldn't with just a blank key. So as the mountains rise, we have these thick wedges of eroded sediment that come off of them, and they're thicker next to the mountains and thinner away from the mountains, right? And then we'll find the fractures in those rocks and later rocks. And so we can tie the timing of the fractures to the timing of the uplifts. And so what we found, and this is, you can go find this in the secular literature out there, is that in addition to the laramide, all right, the more recent uplift of the Rocky Mountains, that there was an older uplift. All right, and so I have here a map of Colorado, and you'll see in the green is the laramide uplift, and it has kind of this northwest trend right across Colorado. And in the blue underneath that is what's called the ancestral Rocky Mountains. And what's really interesting is they're in the exact same spot and have the exact same orientation, right? So the question then is, are these separate events, right, in this kind of cyclic idea of, plates separating and supercontinents breaking up and coming back together and then happening to be in the same, creating mountains in the same exact orientation under the same stresses, several 100 million years apart? Or are these actually just pulses of a single catastrophic event? So that's what we're going into today. So lots of data for the laramide, and while it hasn't been summarized nicely on a single map like the previous, there is a lot of data as well for post-laramide regional extension. And that began in the Miocene and continues to modern time. And it's northwest-southeast trending as well. The fractures within that trend in that northwest-southeast direction. And you can see here, I've just kind of compiled a table that shows the timing as various authors have understood it in their area. And so you've got the Granite Mountains in Wyoming right next to my study area that began collapsing in the Miocene, Pliocene. The opening of the Gulf of California, right? So the Baja of California splitting off from mainland Mexico, right? That an extension happening in the Miocene. You have the Rio Grande Rift, which trends all the way up through New Mexico. I'll talk about that as well. And then the modern stress. So the modern stress is consistent with the paleo stress that began in the Miocene. So we've had one consistent stress regime ever since the Miocene, and no one's going to debate that. We know this because when we go out and drill oil wells, all right, we create fractures. So you have natural fractures that you can go out and measure in the rock, or you can, take a core as you're drilling an oil well and you can see natural fractures. Or you can also create fractures. We call those induced fractures. And those fractures will form in the same orientation as the natural fractures if they're in the same stress regime, right? If the stress regime has changed, then the orientation will change. But what we see in the Rockies is that these fractures are parallel to the stress regime that has been in existence since the Miocene. So any fractures, natural fractures from the Miocene and later, are in the same orientation as these fractures that are created while drilling. And then you also have earthquake data. So the beach ball there that you see on your screen, that's what's called an earthquake focal mechanism. And from that, we can determine that this particular earthquake, it's only a 3.7 magnitude, but enough of a signal there in the data that we could read to actually understand the potential orientation of the fault on which this earthquake occurred. And it turns out that it's an east-west trending fault, which made sense for the collapse of the granite mountains there. So anyway, lots of data out there, just throwing that out. So this is my data from the Wind River Basin, and it's about 1,900 systematic joints. This is a big kind of through-going, just open fractures. There's no slip on them, right? And then you've got all these minor faults, and I had about 45 different locations, and then 39 different oil wells. We have what are called micro-resistivity logs, and there's about 14,700 fractures just from that data set alone. So a lot of data out there, right? And these two maps on the screen, the one with the blue trends on it, which might be a little hard to see depending on your size of your screen and resolution, but the blue trends, those are natural fractures, and the green trends on the top right map are drilling induced fractures. All right, you can see that for the most part, they're very parallel. So the maps in itself, this is a map of the Wind River Basin and its surrounding mountains, surrounding what we call orogens, right? Coming back to that word orogeny, that means the beginning of mountains. So these are mountain chains. And so the dark areas are the old rocks, the pre-laramide rocks and syn-laramide rocks, like the Cambrian, the Permian, Triassic, Jurassic, okay, Cretaceous. And then in the white, what makes up the Wind River Basin right there in the middle, the low part, right? That is the post-Laramide rocks. So the Eocene Wind River and the Miocene rocks. All right. And then in the black lines, what you have is the faults. Okay. And these faults aren't necessarily expressed at the surface. Some of them are. Some of them we know are, just they're massive faults that have been buried as the sediment has been eroded off the mountains. But I don't know if you guys can see my cursor or not, but I'm just going to kind of highlight and talk about a couple of faults here, a couple of big key faults. One is we call the Casper Arch Thrust Fault. All right, that would be along the eastern margin of the Wind River Basin. Okay, and it trends northwest southeast before it turns to more east-west. Okay, turns more east-west, and this would be the fault bounding the Owl Creek Mountains to the north and the Wind River Basin to the south, and we call that the Owl Creek Thrust Fault. And what I found by compiling all this fracture data from outcrops as well as the drilling for gas in this particular area, natural gas, was that the fractures actually tend to parallel those faults. So they're more northwest, parallel to the Casper Arch, and then they turn east-west, parallel to the Owl Creek Thrust. And what's really interesting, right, is that these fractures could not have formed in that orientation during the Laramide, right? So when you've got Laramide faults forming, they're pushing the mountains up over the sediment, and there's compression, right? So they actually cannot form a fracture in this orientation because it's pushing the rocks closed in that orientation. All right, they're not going to break that way. They're just going to get compressed, and you're going to have thrust faults, not joints, not normal faults. Right? And this particular data set is joints and normal faults. All right, and not only are they not in an orientation that would even be possible in laramide age, compression, but they're also in younger rocks that weren't even deposited during the laramide. All right, so these are definitely post-laramide rocks. They're parallel to the modern stress. So we kind of see two things going on, right? We see compression followed by extension. And the really cool thing is that they're linked, all right? And the extension is exactly opposite to the compression. So where you have this kind of unique trends, getting back to that key analogy, right? Where you have unique trends to the fault data in the compressional regime in the laramide, you have a matching set of opposite normal faults. All right. And of course, if you just had, them be one orientation each, it'd be kind of hard to say that they're linked genetically, that they're somehow connected in a mechanism that created both of them. But because there is that parallel and complexity, you can say, all right, there's something going on here, right? This is, there's something here. So this is a seismic line, and I'm sure many of you have, if you're a parent like I am, you've seen a sonogram before. It's the same principle, all right? So what we're doing is we're sending shock waves down into the earth, all right? And they're bouncing off the different layers, the different strata of rock. And so we'll see the layers of the rock, but we'll also see breaks in the layer of the rock, which will indicate where faults are, okay? So this is right across the Madden gas field and up there in the Wind River Basin. And the purple line is interpreted where those laramide age thrust faults are at depth, okay? Now, this particular thrust fault is not big enough to form a mountain range, all right? It got buried, all right? The big mountain range, the big faults are further to the north, okay? But it's got the same structural style to it. The blue line approximates the original, what we call the anticline, all right? Anticline is just a geology word for a fold, all right? An upward fold, an arch. So if you've got a fault that is moving and compressing, right, it's going to bend the rocks over it up, right? Just like you push a rug up against the wall, and it's going to create folds that are up, right? But if you look at this closely, right, you can see right below the arrow here, the blue arrow, there's no arch. Where's the arch? Okay. And so here with this orange line, what you see is the layers are actually flat, meaning the arch has collapsed. Okay. And the red lines here are just kind of, you take a trained eye to see it, but we call these seismic fuzzy zones, all right? They're just indicating where there's a high degree of fracturing. That fracturing eventually, when it gets intense enough, will form a fault through that area. So that would be normal faults, all right, that would form here if that fracturing continues. And that has allowed then the crest of this arch to collapse. All right, so we have thrusting up, all right, the one block of rock is being pushed up over the other block during horizontal compression in the laramide, and then it's collapsing back down that same exact fault under later Miocene extension, okay? So here's a block diagram of what that would look like. So what we can see here is that we have a similar style of uplift and collapse, but the scale of deformation changes between the mountain and the faults underneath the mountains and the faults underneath the gas field, right? So the offset, the vertical offset on the Owl Creek thrust is greater than 20,000 feet. And that would be this big fault here on the left. The gray is the Precambrian granites, what we like to call the basement rocks. Above that in the green is the pre-laramide horizontal strata. It's just laid flat as a pancake, all right? At the bottom of the basin, then you can see that little Madden thrust, just a little blip at the bottom, just sets up this little gas field out in the basin. The orange layer then is the Sin laramide wedge. So that it's real thick next to the mountain range and then thins as it extends into the basin, and all that sediment gets dumped out, right? It gets dumped out right next to the mountains, and then it's not transported as far out into the basin. And then above that, we have the post-laramide rocks that make up the surface in red, okay? And those have normal faults in them. And what you see is right at the margin of the Owl Creek Mountains, All right, you have this collapse zone where you have all these normal faults that tie back down into that thrust fault. Okay, so it's a linked system. So now I want to kind of transition a little bit from Wyoming to West Texas. All right, and West Texas is flat as flat can be. If anyone's going to be a flat earther, I would expect them to come from West Texas or other really flat areas of the world, right? There's no mountains there. In fact, what they like to say in West Texas is you can watch your dog run away for 3 days. Anyway, so there's these two maps that I have here, okay? And these maps represent the depth to the basement. So the depth to the granite rocks below all of the sedimentary strata. So this is Precambrian rocks, all right, and the depth. And where you have the red, it's mountain chains, all right? And where you have the blue, that would be basins. And so the map on the right this is the entire state of Wyoming, and you can see the big mountain chains coming through there and the intervening valleys that filled sedimentary basins, all right? And the map on the left then is the what's called the Central Basin Uplift, and it's completely buried, all right? It's in West Texas, and West Texas, the surface is flat, but there's a buried mountain range under there. And the only reason we know it's there is because it's a prolific oil and gas province. It's called the Permian Basin. So you have Permian Basin kind of composed of 3 sub-basins, or I should say 2 sub-basins, the Delaware Basin and the Midland Basin, separated by the Central Basin Uplift, which is basically just a buried mountain chain. Right, and what you'll notice is that the trend of both of these is kind of northwest-southeast. All right, so it's a very similar trend to the Rocky Mountains. It's just buried. There's a little bit different scale. The Rocky Mountains are a little bit bigger, but there are some faults in the Permian Basin that are just as big as those in Wyoming and Colorado. And so you have mountains up north. Here you have oil fields, right? So there's a lot of seismic data and data from hundreds of thousands of wells that have been poked out here looking for oil, right? So this just kind of is a great overview, right? You can see right here with these maps, the rising mountains and the sinking valleys in between them. So some more seismic lines from down south there. You can see a very similar style of faulting between the Laramide and the Rocky Mountains, and now in the Permian, it's called the Ancestral Rocky Mountains, okay? Because it's older. And so here the purple lines represent those thrust faults. And what you can see is they all kind of terminate below the surface, right? About halfway in these diagrams here, these seismic lines. They terminate into what's called an unconformity. All right, so they brought these mountains up. At one point, they were at the surface, and they got eroded. And so that's that unconformity where they all got eroded off, all right? And then more sediment gets deposited on top. But you'll notice that the sediment that's deposited on top is folded. All right, so take a look here at Dollarhide. Dollarhide's an oil field, the name of an oil field. All these are oil field names out there. And you see this folding above the thrust fault at depth. That indicates that the thrust fault moved, ancestral Rockies, back during the Pennsylvania Permian time. Then it stopped, was eroded, and then it continued folding up the sediments above it. All right, so you're seeing multiple pulses here in this data set of structural deformation. But are they linked? That's the question, right? Is the ancestral Rockies, both in Colorado, which is kind of subtle, and the ancestral Rockies here in the Permian, which is much more pronounced, is that linked to the later Laramide? Are they pulses of the same orogenic event? So in the Permian Basin, you also have Laramide age fractures and Laramide age rocks that are being deposited. So the Benedum Fault in Upton County is an example of one that's been published. You know, they've identified Laramide slip on that particular fault, and they only know of one post-ancestral Rocky Mountain shortening event. So when you see a fracture in Cretaceous rocks, which were not around during the ancestral Rocky Mountain orogenic event, then you know that those fractures have to be later than that. They have to be from the laramide. There's no other possibility that we know of. All right. And here again, now what we see in the Permian is at the surface, all right, we see normal faults. This is my son actually standing at an outcrop here where you have a normal fault. So you have the layers on the left, and then you have this fault zone, and then the layers on the right have dropped down relative to the layers on the left. That's because we're undergoing extension, which allows this one block to drop compared to the other blocks. This is in the what's called the Ouachita Formation, which is Cretaceous in age. And these fractures that we see in the Ouachita Formation are parallel to the Puckett Gray Ranch Fault Zone. So that's shown in blue here on this map. All right, the red lines are just modern roads for orientation. But you can see the Puckett Gray Ranch Fault Zone kind of trends from northwest, and it kind of, there's variability to it, right? It's not just a nice straight line, but it kind of wraps around and trends a little more from northwest to a little bit more west-northwest, right? And what we see in the fracture data at the surface is that they parallel that same trend. Now, the Puckett Gray Ranch Fault is a ancestral Rocky Mountains fault from the Pennsylvanian Permian age. And yet at the surface, we have fractures that could not have happened during that time. They're in younger rocks. You can't open fractures in that orientation under the compressional stress during the Permian. So these have to be a later fracture set that are related somehow to the older fault. Okay, and so this is again a linked system, just like we see in the Wind River range, where you have horizontal compression. Now here it's happening in the ancestral Rocky Mountains, and again a little bit in the Laramide. And then you have extension after that. Here's another seismic line. This comes from the Delaware Basin, sub-basin there in the Permian. And what you see is this thrust fault that has brought up this thick Precambrian wedge. All right, that would be this kind of fuzzy area here that at the bottom that doesn't look like it has any layers really cutting through it. Those are your Precambrian granites. Above that, then you have these horizontal lines. All right, that's your sedimentary rock. And if you look at this, you'll see that some of those horizontal lines are truncated and they thin as they move from right to left across this diagram. Okay, that's because when the fault brought up this mountain, in essence, okay, and then stopped, that started eroding off, and the sediment started filling up until it reached a point where it could actually then cover the mountain and then continue filling above that. But what you see above that again is that you see more folding of those rocks, which indicates that fault moved not only in the ancestral Rockies, but again in the Laramide. And then you'll see that instead of a nice clean arch above this, that arch kind of gets a little wonky in the bright green line. Looks kind of like that arch kind of collapsed, right? It's not a nice, pretty arch anymore. All right, and we'll find actually normal faults. So that's what the red lines are on here, normal faults that are not consistent with the laramide compression, but consistent with a later extension. And that later extension is consistent with the modern stress. It's consistent with the Rio Grande Rift extension. So in this map on the right, you can see that the blue, all right, indicates where the crust of the earth is in extension. Right, that's the Rio Grande Rift, trending up through El Paso, Santa Fe, up through, from Mexico into New Mexico, through this kind of far western part of Texas. And then as you get, further east, kind of halfway across the map, it starts turning green, right? And where it's turning green, you're getting into a strike slip stress, okay? But nowhere do you see a red stress, which would indicate compression. So this is all, modern stress is all predominantly extension with some strike slip as well, okay? But nowhere is the stress such that the rock is being pushed together and one block is being pushed up over the other anymore. That's done. That's over with, right? On the data set, you'll see a bunch of little black lines. Those, again, are drilling-induced fracture trends, all right? And just indicating kind of you can see how the stresses change, right? There's complexity in this. The red and yellow dots represent earthquakes, and you'll see the beach ball diagrams again representing the earthquake focal mechanisms. And again, what we see here, just like we see in the Permian, is that the modern stress is tied back to the faults of the older Laramide system, right? Because they're parallel. All right, as promised, getting into the sandstone dikes in Colorado, the really exciting thing for me at least, and I'm sure many other of my colleagues out there in the creation science world. This is a picture of me about 12 years ago or so, 2011, when a bunch of creationists got together and at the Geological Society of America had a field trip. This is John Whitmore there. And brought in, secular geologists at a secular convention and talked about these sandstone dikes because they are an amazing evidence for rapid tectonics. All right. So the Southern Front Range, it's all Precambrian granite. You don't have a lot of sediment over, say, Pikes Peak. It's a big granitic mass that we call a batholith. And so they did some what's called apatite fission track analysis. And that just gives relative ages, indicating that the margins of the Southern Front Range have dropped lower than its core. Okay, so there's normal faults bounding this massive uplift, just like there is in the Wind River Basin of Wyoming. And these normal faults, of course, how do you get normal faults to uplift a mountain? That doesn't happen, right? The two concepts don't work together. So again, what you have here is you have the older compression followed by a collapse along the edges, a later extensional event, and it's all related, okay? Along with those normal faults are over 200 dikes. Now, a dike is just a really large joint that has been filled with rock. All right, so remember those tectonic systematic fractures that just pop open I was telling you about? All right, now if you get material in there, magma or wet sand that's injected into there, okay, then, and it's a big feature, you call that a dike. All right, it's a filled fracture. That's what a dike is. And these 200 dikes are all parallel to the older faults. All right, so this map here, you can see what's called the Ute Pass fault in the black dashed line that goes right across the slide here and trends kind of northwest, southeast. Okay, that is the fault that brought up Pikes Peak and the Southern Front Range just west of Colorado Springs up over what's called the Denver Basin, right? So you've got older rock on top of younger rock there. That's that Ute Pass thrust fault. Horizontal compression, shortening, major tectonic stress, okay? And you can see it's not just a straight line, but that it kind of wanders around a bit, as you'd expect. Nothing in nature, is perfectly straight, it seems, which is good, right? Because when we compare the orientation of the sandstone dikes, just going back to our key analogy, they are parallel to that older fault. All right, now, if you've got horizontal compression, how in the world are you going to open up these massive dikes and inject sand when you're pushing the rock close? It's not going to happen, right? It just does not work that way. So these sandstone dikes have to be younger than the thrust faults, okay? So these sandstone dikes have to be, and they are, consistent with the modern stress, all right, that we know began maybe as early as the Miocene. Okay. The thing that's really cool about these sandstone dikes, though, is the sand in them. Okay. The sand in them is older. The sand in them came from the Sawatch Formation. The Sawatch Formation is Cambrian in age. Okay. So in the standard model, the sand that is filling these dikes was deposited 541 million years ago. Okay. And then it was injected into these dikes in the Miocene or later, which is 23 million years ago. So that's at least 518 million years in the standard model, okay, that the Sawatch sandstone was not stone. supposedly. Okay, it was soft sediment for all that time, because it would have to be soft in order to squeeze like toothpaste up into these dikes as they opened up. So in other words, the entire geologic column, 520 million years worth, okay, the very lowest, the very bottom, the Precambrian, was soft for that entire time and never turned into stone. A little bit of a stretch of imagination for this geologist. Maybe some others out there buy it. I personally don't. Okay. We know that these dikes opened up in the Miocene. They're consistent with the modern stress. They had to have been emplaced with wet sand. So, okay, what are you going to do with that data, right? Make of it what you will. So here we go. Here's the geologic history. All right, like I said, the Sawash sandstone right down here at the very bottom in the Cambrian, the very bottom of this multicolored column here. Okay, up at the top in the brightest yellow, that's the Miocene. Okay, in the column next to it is where the standard literature puts these different deformational events. So they've got the ancestral Rocky Mountains beginning in the Mississippian, continuing through the Pennsylvanian and into the earliest Permian. Then there's this gap where they don't really know what's going on. Then you have the Laramide in the upper Cretaceous is where it began and then ended in the Eocene. Then you have what's called the Rio Grande rifting above that, beginning in the Miocene and continuing into our modern stress field. Okay. And what I've done is on the right then, I've plotted two regimes. All right. A extensional stress regime in red and a compressional stress regime in blue. And of course, we don't know the exact numbers. There's no way to know the exact numbers of how much the compressional stress was. We don't know how many newtons of pounds of force was being applied during those compressional stresses. So these are then relative curves that I've put on here. And so the green is for the Permian and the red is for the Rockies. And so just to kind of lay it out there for you, okay, there's multiple pulses within the ancestral Rocky Mountains in the Permian, but most of the deformation in the Permian happened in that Pennsylvanian Permian time, okay? But it stayed within that compressional stress regime. In fact, the entire geologic column, it stays within that compressional stress regime. You see a little blip in the Laramide, you see some Laramide movement on these faults, and then it only switches into the extensional stress regime in the Miocene. And it starts off kind of with a bang, and then it kind of slows down, right? You have some initial, major faulting that would have happened, lots of major earthquakes, and then it kind of quieted down, all right? The red curve then is kind of the relative curve, stress curve for the Rocky Mountains. So you have a little blip in the ancestral Rocky Mountains, not so much is going on, but it stays in that compressional stress regime. The crust is in compression throughout the entire geologic column, all the way until you get to Laramide, when it really a lot of compression kicks over. And that's when you build up the Rocky Mountains and they rise to the extent that they are today. And then it too drops off into an extensional stress regime. And so I like to think of this as, all right, you've got the rising of mountains. All right, this would have happened throughout the flood, and especially towards the end of the flood, right? That's the Laramide, right? You're bringing up the major Rocky Mountains in it as a way of draining the floodwaters off the continents into the ocean basins. Right? And so you have fractures in pre to syn Laramide strata, all indicate a single shortening stress, right? It's not flipping back and forth between compression and extension multiple times as you have supercontinents breaking apart and slamming back together, breaking apart and slamming back together. That's not in the rock record. It's not there. And so then you have these, all the data is consistent with the ancestral Rocky Mountains and the Laramide being simply pulses of a single orogenic upheaval, right? That is consistent with catastrophic plate tectonic model. And then after that, you have sinking valleys. And this probably happened as Noah was getting off the ark, and then continued on into the time of Job, and has in fact continued on to a lesser degree into our modern stress as well. So the fractures that we see in post-Laramide strata indicate this regional extension, but it's been localized around some of these pre-existing mountain chains. And then, of course, you see these Cambrian sands that were still wet throughout this whole time being injected into Miocene dikes at the very end of the geologic column, guys. So, all right. That's it, guys, for the presentation part. I'm really looking forward to your questions. We're going to talk in the next episode about how this extension will get renewed and culminate in a lake of fire. So increased volcanism and earthquakes that are coming up. But that's next time. I'm looking forward to it. And I'm open to take questions. And I can jump back to slides or other things too. So,
Ryan, that was an excellent presentation. Time flew by. And we got a lot of audience interaction. So I appreciate the energy and the passion in our live chat. Definitely the kind of presentation that is worthy of a couple views, that's for sure. And I think you said it accurately, that a lot of these geologic features that are best explained by one single catastrophic event, as you've said, to reject that idea would require a lot of imagination, I think, in explaining those features. And especially in the first half of the program, Ryan, a lot of the criticisms or challenges that came in, which I think you addressed sufficiently in your presentation, but maybe in terms of what I like is an elevator pitch answer. If you're in the elevator with somebody, you've only got a couple minutes and they're a skeptic, but they're open-minded. Well, these arguments can all be summed up like this, Ryan. Evolutionists argue that mountain building and plate tectonics demand an old Earth. Before I continue with the question, is it accurate when it comes to those that would reject a worldwide flood, Ryan, those in the conventional field, since they do accept some catastrophism, but they're also still uniformitarians, do they consider themselves actualists now? Like, do they differ from, let's say, uniformitarians in the past?
I would think that they have to, yeah, because it's just so glaringly obvious that geologic events happen catastrophically. I mean, we've got, how many volcanoes going off that we've, seen and observed now. Earthquakes with associated tsunamis, right? And the deposits from tsunamis, and they you have to accept some catastrophic events, whether you're an old Earth model or a young Earth model. It's just the scale of those catastrophic events, right? So I do kind of consider myself a uniformitarian because I do think that the present is the key to the past. But I see that in the present, we have catastrophic events that point us to even bigger catastrophic events in the past, right?
Yeah, that's a good point. And so, in a way, is that them wanting their cake and eat it too? Where in the past, with Lyell, they were kind of strict uniformitarians. But now that we see today, you can't really deny the evidence for catastrophic events today and in the past. And so now they're both, they'll say, because I've seen some in the secular camp that we debate, they'll say, well, we're not strict. We are not the same kind of uniformitarians as they may have been in the past. We do recognize catastrophic events and features and so on and so forth. And so, again, is that kind of wanting your cake and eat it too? Because now they just have the best of both worlds.
No, honestly, I think that's fair. I think that's entirely fair. If your worldview is such that you don't believe in a creator, right? And you don't believe in a historical record that's been preserved by other humans for us today, aka, the Bible and the accounts of the flood recorded there. If you don't believe in that, then you do kind of have to say, okay, all right, I have to accept some catastrophic events, but I'm not going to go to the end that, these creationists go to and say, well, that points to an even bigger one in the past. Which is why I think Revelation comes along and God in his power and his mercy says, okay, hold on. If you don't think that big catastrophic events happened in the past, how about some now? Right? And that's the whole point of Revelation, is to get people to realize, oh, wait, God is the creator. Because, I mean, how can you believe in evolution when you're seeing not just, something like Mount St. Helens going off, but something bigger, right?
Right. And these are small scale examples of what the world wide flood would have comprised, like with Mount St. Helens. And so, yes, I think that's a good answer, Ryan. And I've gotten a sneak peek into your next program on Revelation. So I do want to encourage the audience to make sure that they are here for that. You've got some excellent material. And so, okay, in terms of this specific argument, mountain building and plate tectonics in general, them being uniformitarians, they would reject our position of a single catastrophic flood and event in the past. And so they'll say, well, these processes here, they'll argue that the geologic rates require millions of years for mountain building and plate tectonics. Is this true? What's the best way to engage that argument, Ryan?
Well, the answer to that is yes, they would under certain assumptions, right? If you're sitting at the bottom of the Grand Canyon and all you see is the little tiny puny Colorado River, and you sit down there for a week and you watch it and you measure the erosion rates, you're going to go, well, okay, I've been here for a week. I've measured these erosion rates. They're very, very minimal compared to this huge canyon. Therefore, this must have taken a really long time, right? But if you go back down to that same river in the middle of flood stage and measure the erosional rates, you're going to go, well, okay, hold on a second. I suppose this big old canyon may have happened a little faster than I thought, right? Because obviously when it's flooding, it can erode a lot more quickly, right? So when you add more energy to a system, you can do things a lot faster, which is exactly what creation is saying, is that there was a lot of energy in the system and we had a catastrophic or runaway plate tectonics, and they moved at high rate and created these massive earthquakes that aren't recorded by Noah because he probably didn't feel them. He was cushioned by all the floodwaters as he rode on the surface, right, and was tossed around just by the waves. But nevertheless, they were there. They happened, and we can see them in the rock record.
I'm curious, Ryan, in light of what you're saying there, and there's a lot of good points there. Are you familiar? And if you are, what are your thoughts on these subducted plates, these massive cold plates that you find basically miles and miles deep into the hot mantle that Dr. John Baumgartner describes as being pretty good evidence that this rapid runaway subduction, continental sprint, as some would say, rather than continental drift? Would you see those as being a good piece of evidence for what you're saying here on rapid runaway subduction, Ryan?
All I'm saying here is that the data that I compiled is consistent with that. Okay, I'm not. You can't actually take my fracture data and determine the rate at which things moved. All I can determine from the fracture geometry is the orientation of the stresses, and by that I can determine how those stresses change through time. And so I can tell you that in the geologic column, they didn't change, right? From the Cambrian all the way to the Miocene. And then they did a complete 180 and went into extension. And so that's consistent with the catastrophic plate tectonal model. It's not so consistent with some of the other animations that you'll see out there and the other models of, Pangea, Rodinia, and all these other names that they give to supercontinents colliding and breaking apart multiple times throughout geologic history.
Okay, I understand. And so when you mention the different names in the geologic column, we've got a question here, a good clarifying question, and we have a lot, so let me just make sure I can find it here. I appreciate all the engagement and interaction from our live chat. And so I think it's this one. Travis Statham, appreciate the question. And so he says, when you reference Permian and Cretaceous rock, etc., all these names, are you talking about millions of years and modern geologic consensus? I think already we know the answer to that is no. Or some kind of squeezed in together rocks that are all young?
So, I mean, the geologic column, you can look at it two ways. You can look at it as absolute dates, right? So the Permian is 500, or sorry, not the Permian, the Cambrian is 541 million years ago, right? And you get that from radiometric dating. Or you can look at it and you can say, well, the Cambrian is older because it's below, right, the Ordovician. And that's below the layer above it, right? So you get a relative sense of their age, right? So I do agree, that the Cambrian is the oldest rock unit, and you can use the geologic column in a relative sense, okay, to understand which rocks are older and which are younger. But I disagree that they are millions of years old because I don't agree with the assumptions of radiometric dating, but that's a whole other topic. Um, so relative, that's how I use the geologic column.
I like that. Relative versus absolute. We can even look at the dates in many ways as being relative, and again, not absolute, for reasons we could spend 3 hours on in another show. So I've seen some creation scientists, flood geologists, they'll say when it comes to these different layers, and I'm curious if you would see it the same way or even a similar way or a different way, which is fine too. They'll say that basically we're looking at community. So the Cambrian community, you've got the Permian community, Ordovician community, Mississippian community. And so they'd say rather than looking at it vertically, like we see in the textbooks, you can tip it to the side and view it horizontally. And so now you're looking at all these different communities being buried essentially at the same time rather than evolutionary communities over time. Is that kind of an interesting way to look at it, Ryan?
Yeah, I'd say so. The vertical nature of it, of course, it doesn't exist anywhere that way around the world. But you can kind of imagine if you were to drill a hole over here vertically through those communities, right? And we're talking about the communities, you're talking about ecological zonations, and that would be talking about the fossils, right? But the rocks also change. So you have sandstones, carbonates, and different mixes and ratios of those things that help us define each formation. And you can go around and not only look at the type of formation, but you can go to very different parts of the world and you can kind of get a sense where you are in the geologic column by looking at the type of rocks, even not just the fossils, and going, okay, wow, this looks a lot like those rocks in Colorado. So, okay, we must be in the Cambrian at this point. And sure enough.
Yeah, that's an interesting point. I'm curious, Ryan, when it comes to these mega sequences that we find in geology, could you answer the question essentially, what is the significance of these mega sequences, which is essentially the observation that sedimentary geologic layers are grouped in packages rather than separate entities? And the way that I understand it is they can be correlated worldwide. And if you could elaborate on that, perhaps, Ryan.
Yeah, so these mega sequences, you can talk to Tim Clary at the Institute for Creation Research on that, or he's kind of compiled a lot of that data. And these are pulses, really, where you have some uplift going on. So you've got some rocks that are rising out of the floodwaters as they're rising across the continents, right? And then they cover the mountains, and then those floodwaters might recede and go and be more predominant somewhere else. And at another time, as you've got mountains rising somewhere else at a different time. So the structural, myself being more of a structural geologist like Tim, the structural goes hand in hand with the deposition, right? So where you have the mountains rising, you don't have deposition, and you have the deposition occurring in the basins. And so these mega sequences, talking specifically about the depositional events between the orogenic events.
Okay, very good. So in general, when it comes to these sedimentary rock layers, Ryan, that extend over entire continents and can be matched and clearly indicate a single catastrophic event, you're not convinced by those in the local flood camp, professing Christians, but they hold to old earth creation and the local flood theory. They'll say, well, okay, yeah, these are catastrophic events. So kind of like we talked about at the beginning, Ryan, to set the stage for the discussion, that they do hold a uniformitarianism, but with some catastrophism mixed in. And so they'll say these are local catastrophes making these geologic features still over millions of years rather than a single catastrophic event. But you're not convinced by that.
No, No, there's just too much going on in the geologic record, and too much connectedness and interplay that you can see between different areas, that it has to be really one event. And honestly, if you're gonna believe the Bible, why not believe all of it?
Right. Rather than just specific parts. I like how you said that, connectedness and interplay. I'm going to steal that from you. That's good.
Sure,
and that makes sense because, yeah, all that connectedness and interplay and the fact that they stretch over entire continents means that it couldn't have just been many local catastrophes over millions of years. No, it has to be one catastrophe to explain that correlation.
Yeah. If you saw like something being deposited over here and something over here, and they're completely different, right? There would be no reason to link them up. But when they start having similar characteristics, and maybe they've got similar patterns to the types of fossils and the order that those fossils are deposited, right? Which is what we see in the geologic column, even in the secular model, right? Then you start going, okay, well, this is too linked of a system. This is like, key and lock fitting together. They're made to go together.
Yeah, I like that. There's linking. It's like a key and lock. They're made to go together. That's really good. It's a good rebuttal. Okay, so the next question comes in from, let me see here. We've got several challenges, but there's one here from Reboot. And again, we've had a good mix of questions, so I don't want to lose him. Here's an interesting one. So Reboot says, why should one believe that a global flood caused the mountains to form in a year, and yet the Earth's core, which is around the same temperature as the sun, takes longer than the young Earth Cretaceous universe? I'm not sure I fully understand that question, but Ryan, do you have any thoughts on that?
Yeah, I'd say that's a little bit of an incomplete thought there. I'd like to know what he means by longer than the YEC's universe. I personally, believe that there was something here before life, that there was a rock here, and we don't know how old that was. And I'm not about to say that it's billions of years old, because I don't believe in radiometric dating. And I find no scientific basis for it, having taken classes on isotope radiometric dating. And so, who knows how old it was, but the Bible's clear. There's something was here, right? The Spirit hovered over the surface of the waters. There was something here. It was called the tohu wabohu, the empty and void. But and then God created, and then you had, the beginning of time here in our time domain as we understand it. And so I believe in like a young creation, not necessarily that the core of the earth is young.
Okay, I appreciate that, Ryan. That's helpful. Travis Statham, considering that the Bible is a faith-based book, what utility does it have to geology, a science-based epistemology?
I honestly put all my faith aside when I went and studied it with some creation universities and secular universities as well. I put that aside and it's like, all right, I believe this. This is my faith, but, can I defend it logically, scientifically? And so I've spent a lot of time looking at the data for what the data says and checking the assumptions. And when you check the assumptions, you just, well, okay, do you believe that one, or is that one too much of a stretch for me to believe? And all interpretations are based on some kind of assumption, all right? And all interpretations, even interpretations of prophecy, right, are based on some kind of assumption. Interpretations of what the Bible means are based on some kind of starting point. Interpretations of evolutionary models have a starting point. And so if you're comfortable with those starting points, then you proceed, with your model. And so I'm personally not comfortable with the logic that would lead someone down the path of evolutionary thinking. And so everything I see is consistent with the historical record found in the Bible. So for me, it's not a faith-based thing at all. It's a logic and reason-based thing.
Yes. Amen. So do you think that somebody could come at the data, the geologic data, without any real presuppositions or even, let's say, a faith-based starting point from the Bible, look at the data hopefully they're being open-minded and conclude, okay, there must have been some kind of worldwide single catastrophic event that formed most of this geology. Or as some critics would say, oh, you got to first start from the Bible to even come to that conclusion, Ryan.
Yeah. No, I think most logical, rational human beings, and if they were brought up in such a way that they're isolated from the indoctrination of evolution, right, and just looked at the data for themselves, that there's no other conclusion that they could come to, but that there's something bigger out there, right? There's irreducible complexity, epigenetics, so many different things that point to a creator if they spend enough time and were actually learned in these and how these things really work, and the philosophy of thinking, and how to make logical conclusions, and build step by step, right? If they were trained on that in the absence of any indoctrination evolution, they wouldn't even come up with evolution.
Yeah, that's a good answer. I agree with you there. And so I believe in model building. I think it's good to debunk evidence for evolution. We certainly do that here, debunk old earth ideas, but we don't want to just do that. We want to model build and come up with a superior explanation. And so a lot of that does have to do with the gold standard of science, making testable, falsifiable predictions. And I think of this, and so I say it because of Travis's question here, glancing over it. And so he's wondering, I still don't see how the global flood has any model that, and in the young earth creation world, there's a few different models anyways on the flood, that provides falsifiable predictions. Are you saying that all changes we see today don't exist? Ryan, what are your thoughts on that?
I'm not sure what he means by all changes we see don't exist. Of course, changes exist today. Yeah, the catastrophic plate tectonic model developed by Baumgartner hypothesized that there would be cold plates down deep all the way to the Earth's core. And that was, I mean, he was running this on supercomputers and with his model before we were doing seismic tomography that found these deep plates, right? So if they had been able to find that these deep plates were hot, that would have falsified the catastrophic plate tectonic model. So absolutely, creation global flood models have provided falsifiable predictions that have not been falsified, right? In fact, they've been supported and validated by later findings.
Yeah, that's a great response. That's a testable and falsifiable prediction right there. Yeah. In the world of the young universe, Dr. Russell Humphreys has made several predictions that have shown themselves to be true. Genetics, we could go over many predictions there as well. In terms of the cold slabs, from my understanding, Ryan, that if these plates really were just moving a few centimeters or inches per year, these snail pace movements, then they should have essentially assimilated to where they, as you said, they would be a lot hotter or even completely melted. But the fact that they're cooler, and how they tell through seismic tomography, are they just looking at, are they comparing density of those to density of rock at the top, basically at the surface?
Density and a lot of other fancy calculations that I don't understand. That's the geophysicist realm. Yeah, they're looking at the data that they get back from seismic waves from earthquakes that have traveled through the interior of the Earth, and they're mapping that out. So we've got a plethora of geophones that are listening to those earthquake signals all around the world, and they're able to start mapping out in pretty good, astonishing detail what's going on in the interior of the Earth.
Okay, so very simply put, for the audience, if those were taken down there millions of years ago through continental drift, then they should have warmed up or melted. The fact that they're cool or cold suggests that they were taken down there just thousands of years ago through catastrophic processes. So that is a really good point there.
And we know that because of the seismic waves travel at different speeds in different densities and different temperatures and different types of rocks. So once we get enough geophones out there that are all recording the data at different time, right? The seismic waves arrive at each geophone at a slightly different time, depending on the distance and the type of rock it's gone through. Once you get enough data, you can start mapping it out. So
that's a really cool science. Wow.
Yeah.
Okay, so here's a question from one of our biggest fans. Creationist crybaby. So you're going to be evolutionist crybaby soon after all these presentations. I'm just kidding. We like to tease each other. So he's wondering, Ryan, and I appreciate the question there, CC. Can you explain? He says also, so there must be something before that. Let me see. Oh, here we go. We got enough questions to keep us busy till same time tomorrow, Ryan. So he says, Ryan, please explain how the eastern margins of North and South America match the western margins of Europe and Africa, and all match the shape of the highly volcanic mid-Atlantic ridge.
Yeah. I haven't studied those areas in depth, so I don't want to get too far out and speculate too much, but I'll just say that, you know, logically, when you have that much interplay going on between those systems, they have to be genetically linked. They have the same root cause, right? And so, you know, statistically, logically speaking, they are connected. To tell you the details of that and how that worked, I don't know, and I honestly don't know that we have a really good sense of that in the creation science world yet.
That keeps what the technical aspects of your presentation, Ryan, the way you explain the interplay between these different systems means they have to be linked or connected into one, basically, as I understand it, single catastrophic event. That makes a lot of the technical aspects of what you're saying as understandable, but it also provides a good rebuttal to a lot of the critics' possible challenges. And so this goes to the also part of it now. So he says, also explain the matching fold belts in structure and age in Appalachian Mountains, Little Atlas Mountains of Morocco, Scottish Highlands, and there's a couple others. Are you familiar with those, Ryan?
Yeah. The Appalachians are really one mountain chain from, you know, the Georgia on up through Maine, Nova Scotia, Greenland, and right straight over to the Scottish Highlands. Yes, they're all part of one mountain chain that it was split apart. I think what we don't have a good sense of yet is if those were possibly pre-flood mountains, because they do appear to be older. They're a lot different than the structural styles that we see in the Rockies, for example. So something different was going on there, potentially pre-flood. There's a lot of Precambrian faulting and within that. So, but they're definitely linked.
It's a good answer. I appreciate that, Ryan. Here's one of my own questions that I'm curious about, because you working in petroleum and oil, basically a major challenge for years and years that I've seen, including I see this in big debates on the flood, and informed evolutionists, they'll say, well, all of our fossil fuels, coal, oil, natural gas, they're all formed by geologic processes. And because of this, they'll look to a specific process called basin modeling. And they'll say it has to do with radiometric dating as well. But essentially, they'll say finding the natural gas and oil requires deep time. Like it's the assumptions of evolution and uniformitarian thinking that allows them to find oil, and oil makes companies billions of dollars. And so, you know, that's the utility of evolution thinking. But they'll say that the young earth creationist position can't do that same thing. Are you familiar with that point? And secondly, what would be a good way to address it, Ryan?
Well, I'd be curious to know if they found as much oil as I have. So
probably not.
It's a rather silly argument, because the time at which the absolute date absolutely matters zero when you're going out to find oil. It's a relative date. As long as you have the relative date and you can map the different rock units in a relative sense, who cares what the exact number is? It really doesn't matter. When it comes to oil, there are two different kinds of oil. Okay. There is terrestrial sourced oil and marine sourced oil. And one comes from algae and the other comes from bacteria. So both of these oils come from a tremendous amount of algae and bacteria that has been buried along with the sediments, cooked at high pressures and temperatures, and converted into hydrocarbons. If you think about it, cellulose and sugar, these are all molecules composed of hydrogen, carbon, and oxygen, which another word for petroleum is hydrocarbons, right? So these are broken down biological molecules, and we know that they come from algae and bacteria. Well, what better model do you have for generating vast amounts of bacteria and algae than warm oceans from the breaking up of the fountains of the great deep, filled with lots and lots of dead things? I mean, that's where the oil came from. It's the flood. That's why we're not creating more of it. It's not something that's happening today, just like we're not forming fossils today. You have to have very special, very unique conditions in order to create oil. And yeah, relative dating will help you, but just no need for millions of years at all. Again, it's a rate thing, right? If you can bury it quickly and get it down and start cooking it right away, you can decompose those biological molecules into oil very quickly.
Okay, so it was more so just an assertion, not backed up by anything, to continue saying, oh, well, we from the evolution's deep time starting point can make these predictions, know where the oil is, make money from it. So are you basically saying, as creationists, we could look to those ages or those sequences, relatively speaking, not in an absolute sense, and that is really enough to find the oil and benefit from it?
Yeah, absolutely.
Okay, very good. And then the second part to your question, answer, I appreciate, because there's prominent old Earth creationists, and they all agree that this challenge, which I'm about to put forth, is a precluding challenge, they like to say, as in it just makes young Earth creation impossible. And they'll say, okay, we got all this oil, this natural gas, all this coal, but in light of how much plant material and algae and dead organisms it would require to even make all that, whether it's rapid or over a long time, in the past, in a young Earth model, there simply just wouldn't be that many animals, that much plant material, that much algae to make all of that. What would be a good way to engage that challenge, Ryan?
Okay, well, that's their assumption. I mean, that literally is the definition of assumption. Who's to say that there is no possibility that there wasn't more plant life at one point, and that the Earth wasn't warmer and had more carbon dioxide in the atmosphere to support more plant life, and that the maybe there was more land mass compared to ocean mass, in which you could grow more, or maybe these swamps grew out like the sphagnum peat swamps in the boreal forests up north. They just kind of spread out over top of the water. In fact, most of the photosynthesis on Earth today still happens in the oceans with plankton. So there's a lot of potential that before the flood there was a lot more biological life going on. I think that's indicated in the fossil record. I mean, you've got these massive dinosaurs, right? Herbivores. What did they eat? There had to have been a lot more vegetation to sustain these massive beasts. So there's no reason at all to assume that in the past there was less vegetation, not enough to form coal seams. The data points to the exact opposite, that there absolutely was.
I find it interesting that these are their so-called best challenges, and like you said, they require a lot of assumptions. And a lot of people, I think, confuse, Ryan, that at the flood we have 2 of every kind, 7 of some, depending on how you interpret the 7 and 14. But let's just say 2 of every kind. But at creation, it's not like God just created 2 dinosaurs, 2 dogs. I imagine he would have created populations of animals. The Earth would be teeming with animals, put into fully working and functional ecosystems. And so that pre-flood, and then you got a couple thousand years to vary and speciate and so on and so forth. So as you've said, there'd be more than enough life, organic life. The Earth would have been created probably 90% green, maybe, like you said. There'd be a lot more land mass then than there is today. And yeah, I think that's a good, and you've pointed out in your previous answer that oil, for example, could be produced rapidly as long as you have the right conditions.
And coal as well. They can produce coal very quickly in the lab under the right conditions. So you can do it naturally as well.
So is this why some and I enjoy reading the technical literature in the world of young Earth creation. Some creation scientists have proposed these floating forests, which have been would have comprised a lot of vegetation, diverse creatures. Would that be one of the reasons, perhaps, that they invoke floating forests to provide more plant material, basically to make coal and oil and so on and so forth?
Yeah, that into account for the, thick deposits of coal that are found in marine environments, right? And so whether that was a living raft of a floating forest or whether that was more akin to what they saw in Spirit Lake after Mount St. Helens with all the legs just blown out and floating in the lake, either way, right? I'm not gonna, and probably both. That's just one of those things where each individual location is going to have its own kind of unique, parameters, and there's a lot of room for very interesting, fascinating science to happen within the biblical model. There's a lot of space in between the lines of the historical record, right, to interpret what's going on.
Right, that's a good answer. So here's an interesting one here. I see this one frequently. Travis Statham, appreciate the questions here and all the interaction. This is what we want. Are stories about a global flood from non-ANE, ancient Near Eastern countries, possibly true if only 8 people survived the global flood? Does this mean all of these stories are made up and wrong except yours? And I've also seen critics, Ryan, say that basically the Genesis flood story was copied from one of these earlier, they would say, flood stories like the Epic of Gilgamesh.
Yeah, I think a lot of secular scientists jump through a lot of hoops to kind of say that some of these stories are older than the Genesis account, and I'm not sure that data is actually supported. They talk about this Proto-Canaanitic alphabet, and just to get away from saying, well, maybe it was the Hebrews who actually developed the alphabet, and started writing these stories down first before anyone else. But the fact that there are these stories all around the world indicates that there's a common truth to them. It's the details that are preserved in the Genesis account that really give it the credibility. It's not only just telling a legend of a time at some distant ancestor that was saved from this flood, and it's the detail of, it wasn't just an ancestor, right? It was, here's the name of my father and his father and his father and his father, and this is how long that they lived, and here now is when this happened, and it happened, and this is the size of the boat, and this is the geologic things that happened, right? The fountains of the great deep breaking open. You have a transgressive phase talked about where the flood risers are rising, and then a regressive phase where the flood waters are sinking off. The details of all those are just, you do not find that level of detail that can be backed up through scientific investigation in any of the other stories.
That's a good answer. The secular world, the critics, they don't like the fact that ancient civilizations, written history, all go back right to where we would say the flood is 4,000 to 5,000 years ago. Yeah. And in light of what you're saying, many people have done it. Compare the Genesis flood story with all these different flood narratives, and you can see that the obvious common source or common ancestor to all those other flood stories are the Genesis flood. Yeah. And that's why you can see a lot of exaggerations and obvious mythological aspects in the other flood stories. But yeah, they would all go back to an original source rather than the Genesis flood copying itself from that one. And so, okay, here's the next question. This is an interesting one. Did the global flood kill off our early human ancestors like Australopithecines or Homo erectus? Well, I guess that depends how you would view them, as either post-flood or during the flood. If they're post-flood, there's not really a problem there. Why weren't they saved on the ark? What about the Neanderthals or Homo naledi? Ryan, what are your thoughts on that?
I mean, that statement is so rife with preconceived assumptions in there that that there are early human ancestors, when in fact Neanderthals and humans live side by side, and
Right.
and clearly in post-flood rocks. So that's just it's coming from a place of some other model, right, is being imposed on that particular question.
Yeah, I don't know how you could have a model that says so-called hominins like Naledi and Neanderthal and Erectus or Hobbit, who lived on an island of Flores, were pre-flood. But I wonder, Ryan, when it comes to hominins like Neanderthals, we
Mhm.
are so confident, most of us as creationists, that Neanderthals are post-flood. But if someone were to ask why, what would be a good way to answer that?
Well, you go to where they're found, right? They are found in caves
Mm,
that are thick deposits full of fossils. Those fossils don't form under geologic conditions today. Massive caves don't form under geologic conditions today. Um, and I mean, you have to have a lot of fluid to carve out these caves and create these cave features. You have to have even more fluid to lay down the sediments that the caves were in before they formed. So it's definitely post flood. There's no way around that, unless you're going to appeal to some kind of local flood model. But
yeah.
then how do you get deposits of that scale that stretch over vast distances, in which these caves and the Neanderthals are found in?
So those caves that the Neanderthals are found, that's a great answer, that they're found in, they were
Mhm,
rapidly produced during
mhm.
the global flood. We find that they buried their dead. So don't you think if they were pre-flood, wouldn't those burial sites essentially be wiped away or
Yeah,
uh,
yeah,
catastrophically dumped somewhere else? Perhaps it'd be more
exactly.
messy. Yeah.
Yeah.
So if you were to say, well, this was from pre-flood, you'd basically have to have during that year the caves rapidly forming, and then the a relaxed stage, perhaps Neanderthals would go in, die in it. Yeah, it would be too much of a stretch to. So
Yeah.
I'm curious. I see this all the time from old Earth creationists, and I know you're passionate about the scriptures, and so they'll point to verses like 2 Peter 2:5, which says, "And spared not the old world, but saved Noah, the eighth person, a preacher of righteousness, bringing in the flood upon what? The world of the ungodly." I see this all the time. They'll say, well, the flood was universal to the world of the ungodly, but people weren't living in Antarctica or the Americas or Australia at that time. So that
Mhm.
means the flood, although universal, not worldwide, because it just had to wipe away that world of wicked men. Ryan, what's a good response to that?
Right. I mean, in 2,000 years, well, 1,656 between Adam and the flood, you had people that were living to like 900 years old and more, and having 30 sons and who knows how many daughters. And so there was a huge population that probably was spread over the entire globe. So yeah, the wicked that were destroyed, probably not a local community.
Yeah, if you're an old earther, you'd have to say like they're really local. And then what happens if there's just a couple of isolated pockets of people? They decided to leave that local community, which happens all the time, start
Hmm.
their own little tribe. Did they survive, or did God just somehow? It really is stretching the imagination, isn't it, Ryan? These
Yeah,
old earth
yeah.
interpretations. And then they'll have to say it's basically a coincidence that the Bible says the earth was overspread by Shem, Ham, Japheth, and their three wives. And the genetic data actually confirms that. So we have the geologic data and the genetic data both confirming the reality of the flood. This comes
Exactly.
in from Praise I Am. Appreciate the question, brother. Were there dinosaur eggs on the ark? So, in other words, from the young earth creationist perspective, God saved two of every kind. Do you think he just brought babies of some of the dinosaurs, maybe dinosaur eggs? Ryan, I'm curious your thoughts on that.
Well, the average size of a dinosaur was the size of a chicken. So there's a lot more small dinosaur species than there are the really big ones. And there's also the thought that a lot of the larger dinosaur species, if man lived 900 years, what about lizards that keep just growing and growing throughout their entire life. Maybe those
Mm.
smaller species are the same as the larger species. There's just, hey, scientists, when they like to, they like to pat themselves on the back and be like, I discovered a new species. Well, did you really?
Yeah, you're not going to be famous for the 50th T-Rex fossil that you find. But if
Yeah,
you find a fossil where there's enough variation in it, Ryan, you can give it another name.
yeah,
Sometimes the smallest variation too. Now you're
yeah,
famous, right?
yeah, yeah.
Yeah, and
So
that's
as far as eggs, maybe. I mean, there was a male and a female, so maybe they had eggs while they were on the ark. But again, does that matter? It's a cool question to think about.
right.
One that I'm sure will get answered one day. But
Yes, I'm sure we'll see the tape in heaven one day on how
yeah,
exactly things were done. But
exactly.
what they don't realize, in order to falsify or preclude, like they like to say, young Earth creation, when we're
Mhm.
dealing with historical science, for them to put forth a challenge that precludes the flood or the young Earth creation model, they would have to refute every single possible story. So yeah, I mean, possibly there are dinosaur eggs on the ark, or possibly this, possibly that. So when it comes to historical science, we could have a lot of ideas that work, that are reasonable. And so, okay, I think we got one more question here. Let me see. Yeah, here's one that I hear frequently and that I'm curious as to your thoughts. Ryan, critics of young Earth creation argue that worldwide floods can't explain clean, pure sandstones. For example, the St. Peter's sandstone. They point out that only rivers and beaches can create pure sandstones. What would be a good response, Ryan?
Um, well, there's some pretty massive dune formations at the bottom of the ocean. And in fact, some of the largest dunes on Earth are at the bottom of the ocean. So the oceans are a really good way of sorting sediments and winnowing them out, getting rid of all the fine particles, the clays, the silts, and leaving behind just a pure sandstone. In fact, things like the coconino have been shown to be actually not what geologists call aeolian, which is deposited in a desert environment, but actually deposited underwater. So yeah, absolutely, the worldwide flood can explain clean, pure sandstones. It's all a question of how far you transport that sediment and how much energy there is. Right, the further you transport it, and the more energy you have, the more you are to clean out those finer particles and sort into pure sandstones and pure clays. And it requires energy. And the only way to get that kind of energy is in a global flood, not in slow, gradual processes.
I love that answer, because the critics will oftentimes say, oh, there's just so much energy and heat and pressure produced from the flood that the flood can't be true. But yet, those could be features rather than bugs, like you're saying, that
Mhm.
heat and energy that can be utilized to form a lot of the features that they say can't be formed in a young
Yeah,
Earth creation
exactly.
time scale.
Yeah. Yeah, and so they talk about these heat problems and stuff, and I think, well, hold on, wait a second. If you have a model that is going to put out a lot of heat, isn't it reasonable to also think that that energy could go back into the system in another way, right? In the formation and the winnowing of pure sandstones, for example, right? I don't think the energy left the system, right? It's just been redistributed. You see that in chemical reactions all the time, where it takes a lot of energy to break bonds, chemical bonds, but then it also uses a lot of energy, which is why we have chemical reactions going on all the time without creating explosions, right?
Yeah, it's a great response. I mean, look at all of this so-called coal, oil, and natural gas that the old Earth creationists say we can't explain because there's not enough of that. Apparently, that's their assumption. But yet, as you've said, heat, pressure, we've seen in the lab, coal and oil, from my understanding, produce rapidly.
Mhm.
Okay, so that redistributed heat and pressure and energy during the flood could have rapidly formed a lot of this coal. And I know the critics are just going to tear that apart, but it's a possibility. I don't see why a lot of it couldn't be, sent to the core. Do we know how hot the core was, Ryan, during the pre-flood world? Maybe it heat it up to what it is today? Because a lot of that heat was taken down there.
That's a good question for John Baumgartner.
Yeah.
Don't ask me about the core of the Earth.
I'm just thinking out loud because they always bring up the heat problem, and so I think of different sources that heat could be utilized for. So Lynn Mitzi, bonus question here just came in. Did they not feed or need to feed animals on the ark because these fell into a hibernation?
Entirely possible, I suppose. I mean, I wouldn't have thought that hibernation really began until, you had animals trying to adapt to real cold temperatures. But in a crisis situation where, there are animals out there like that giant toad, I think it is, in Australia, right? It goes into a hibernation when it's in a drought condition. So it's entirely possible that, animals went into hibernation as a way of getting through it. I'm sure that there was plenty of room for food on the ark. It's a massive ark, and you got to remember the number of species today is, again, right? Everyone wants to name a new species and define a new species, but a lot of these things are just variations of the same biblical kind, and so probably a lot fewer representative species were on the ark, leaving plenty of room for food and other necessary things.
Yeah, it makes me wonder if the potential for hibernation or migration, they were latent abilities, and they were triggered because of the ark and the flood. And so, Ryan, to wrap things up, because I'm really excited for our next program next month. This one flew by. You're a wealth of information on this topic, so I appreciate you engaging these questions here from a variety of different issues. Can you give us a sneak preview into the geology in Revelation? Because some people might be wondering, Revelation, geology, the flood, like geoscience, how do these things relate? So maybe let's wrap things up with a bit of a sneak peek into the importance of geology when reading Revelation.
Yeah. So this might come as a surprise, but the most common Greek word in Revelation is theos, right? God. But the second most common word in Revelation is ge, the Greek word for earth, from which we get geology, right? The study of the earth. So Revelation really is a book about geology. And I personally believe that the central theme of Revelation is given by the first angel's message in Revelation 14:7. Fear God and give glory to him, for the hour of his judgment is come, and worship him who made heaven and earth, the sea, and springs of water. So I think what's coming and what's predicted in all these geologic events that are hinted at and alluded to in Revelation is a period in Earth history, right up at the close of Earth's history, in which God is saying, hey, guys, I'm not just some deity out there in the universe that doesn't care what's going on, right? I'm still all powerful. I created the world. I care about you. And there is geologic calamity coming on the earth, but I'm going to save you out of it, right? Just like in the days of Noah, right? God prepared or had Noah prepare an ark for the saving of humanity. I think that these geologic things that are coming, the earth is going to be completely deluged, this time by fire, and that the only place of refuge, our ark, is going to be the New Jerusalem, that God is preparing specifically to float on the surface of that lake of fire, in essence, right? And to preserve a remnant from that destruction, from that utter destruction, right? And outside is complete destruction. And if you're not willing to, get into the place of refuge, the place of safety, into the presence of God, and live in love and peace and harmony with your fellow man, versus you just want to hate everyone and be outside and be anti-God, you're not going to be in the place of safety. You're going to get destroyed, right? If you're not willing to heed the warnings. And I think that's all Revelation is. It's not a punishment from an angry deity. It's just, here's a warning, here's another warning, here's another warning. They're increasing in intensity. And Revelation, when you look at it from a geologic perspective, you can see how one thing kind of leads to the next and the next and the next. And it's actually just like a chain reaction that just culminates in that final part of the story. And really, it's all to drive the theory of extinction, the theory of evolution to extinction, because there's no way you're going to be an atheist pounding on the doors of the ark, right? There's no way you're going to believe in evolution when God and the New Jerusalem are right there. It's going to be so obvious that those who aren't saved don't want to be saved.
That's right. Amen. I mean, so many great points there that we get to touch on and
Yeah.
elaborate on in next month's program. And so you're saying this judgment by fire, Ryan, it's not just a local judgment coming to like a single city near you. This is like a worldwide, universal judgment by fire.
And then it's not a punishment. It is a natural thing. It's a natural geologic consequence that God is rescuing his people who want to be rescued. He's rescuing them from that.
Isn't it amazing that where we get some of that 2 Peter 3, that the scoffers deny the creation, the fact that the earth and heavens were created supernaturally? That's universal to every degree. And then your third thing that the scoffers deny is this judgment by fire that you're going to talk about, which is worldwide, universal, catastrophic. And what's the middle? What's the second one they deny? We talked about that today. The world that then was being overflowed with water that perished. So your local flooders, in my opinion, are very inconsistent. They're like, well, okay, 1 and 3, those are universal, worldwide, covers everything. But that middle one, no, that was local over here in the Middle East, little region. But to be hermeneutically consistent, as you know, being a researcher of the Bible, all three fit together.
Yeah, absolutely. Looking forward to it a lot. So it would be a lot of fun.
Me too. That was a great teaser, Ryan, here in our live chat. Appreciate it to my faithful moderator, Doki Doki. Check out Ryan's book. Yes, please do. Remnant Rendezvous. And I'll make sure your channel's linked, brother, in the description box. You were also commenting earlier at the beginning. So please, everybody who watches this now and also later, as it will be available right away, please go give Ryan a subscription. He's got a lot of great videos, good mix of revelation. And we have a lot of fans of Revelation here too. We do discuss a lot of end time theology. Yeah. And so, you know, I know people are going to love your channel. And right here, we've got your website and your YouTube channel. So go give Ryan a subscription.
Yeah.
And
thank you.
Okay. Oh, there we go. Appreciate that. It makes it easy. Thanks, everyone. Yeah, some great activity and engagement in the chat, live interaction. I appreciate all the questions that have come in. Even to our critics, we want to plant some, you know, we could win arguments all day, but it comes down to winning souls and saving people from that coming judgment by fire. Ryan, any final words, final thoughts?
No, just thank you again, Donny, so much for all you do and putting these out there and spending so much time doing it. It's really appreciated. So keep it up.
All right. I appreciate those kind words, Ryan. I know how busy you are, so I appreciate you giving us time for this program. And then also next month, so about a month from now, we are going to get part 2 of this epic series. So tonight, Noah's flood, rising mountains, and sinking valleys. Thank you, everybody, for tuning in. I hope you all had as much fun as I did, and we will see you soon. God bless all. Standing for Truth is out.